So now moving to the third classification of open channel flow is that classification based on turbulence. So now third one is classification based on turbulence. Now on the basis of turbulence you can classify in three subcategories. First one is your laminar flow. Second one is your transitional flow. And third one is your turbulent flow. Now, what is the difference between laminar, transitional and turbulent flow? We will deal one by one. Whenever you are talking regarding the laminar flow, all these terms you would have encountered when you have studied your fluid mechanics, but still if you haven't, never mind, we will discuss in brief what are the things which are important for us. So, in this laminar flow, what happens is the flow occurs in the form of layers. Fine, we assume that the flow occurs in the form of layers. The streamlines are parallel. For laminar flow, there is almost negligible turbulence and there is not much undulations as well. Fine. So, can I write all these things? Laminar flow I can write streamlines are parallel. Low velocity, not much undulations, and flow occurs in the form of layers. Fine, although there will be difference in velocity, but we assume that the flow occurs in the form of layers in the case of laminar flow. Now, before moving to the turbulent transitional flow, we will first deal with the turbulent flow, then we will move to the transitional flow. Now, what happens in turbulent flow? It is almost the opposite of your laminar flow. Like first what you dealt in laminar flow is that streamlines are parallel, while in case of turbulent flow, streamlines are not parallel. Similarly, you have not much undulations, while in the case of turbulent flow, there are lot of undulations and there is lot of turbulence as well. The reason is the flow occurs in a haphazard manner, that is, it is not occurring in the form of layers, it is occurring in a haphazard manner. I will show you how. The flow occurs like some flow occurs like this, so this is the flow which is occurring. Fine, some flow occurs like this. So, this is like a haphazard manner the flow occurs. This roughly I have drawn it, do not need to draw, just for your explanation purpose. So, in turbulent flow there is lot of undulations, there is lot of turbulence and the streamlines are not parallel as well. So, I can write lot of undulations, lot of turbulence, streamlines are not parallel. Streamlines are not parallel. Fine. Now, coming to the transitional flow, it is partly a combination of laminar flow and partly that of your turbulent flow. That is, the flow is little bit undulated, sort of, you can say, that is the case of your flow is little bit undulated. It is in between to that of your laminar flow and turbulent flow. I am not going in detail because that is not at all required. Fine. Why there is a need to study based on turbulence, that I will tell you, but before that you should know the main things about laminar flow, that is low velocity, streamlines parallel, similarly for transitional flow and for turbulent flow. Now, this I told you the definitions regarding all three. Now, could you tell me how could you identify, or if you have been given the parameters, various parameters, could you tell me whether the flow will be laminar or turbulent? Come on, just give me the answer. Is there any way, is there any number through which you can tell me whether the flow is laminar or whether the flow is turbulent? Come on, fast. So now what happens is Reynolds number. If you haven't come across the word, I will tell you. Reynolds number is the number with the help of which, so you can classify whether the flow is laminar or turbulent flow. So now, Reynolds number is basically Reynolds number is basically written as RE in short form. Fine, it is the ratio of your inertia force to that of the viscous force. So, we are not going in the derivation part, it is not at all important. What end result you get is as rho VL by mu. In books you find this as L, or you can see it as LC. Fine, I will write the meaning because I told you earlier some students would be knowing this, but for students who do not have any idea about open channel flow or neither they have studied FM, I am going from the base. Fine, rho is the density, generally it is the density of water, but if you have any other liquid also, density. V is the velocity. LC, this LC is important. LC is your characteristic length. So, this LC is your characteristic length. Fine. And here this mu. Mu is your dynamic viscosity. The relation between this dynamic viscosity and there is one more term, that is nu, which is your kinematic viscosity. Fine, this is nu, which is your kinematic viscosity. So, how is this nu and mu related to each other? It is like kinematic viscosity is equal to dynamic viscosity divided by rho. Fine. In this way, if you have been given kinematic viscosity, you will multiply by the density, you will get the dynamic viscosity. Fine. Now, coming to this LC, that is your characteristic length. What is this characteristic length? What happens is the Reynolds number is used, as I told you earlier, as an index of classification, but it can be used both for pipe flow as well as for open channel flow. However, the number, it will differ for both of them. I should tell you this Reynolds number when we were differentiating in pipe flow and open channel flow, but because it is in this part, classification of open channel flow, we will deal it here. Fine. So, now characteristic length in case of pipes. In case of pipe flow also you can say, it is your D. Pipe flow case, this is your diameter. In that case LC is, in place of LC you put the value of your diameter when pipe flow is concerned. While in the case of open channel flow, characteristic length is your hydraulic depth. You have to remember this because I will tell you later why there is a need for this hydraulic depth. See, this is also denoted by D. And you know that I told you in the geometric parameters, hydraulic depth is the ratio of wetted area by top width. Fine. So, now I told you regarding what is Reynolds number, what is the various parameters, what you name it, all these things. Now comes the question, what are the values of the numbers which differentiate open channel flow and to that of the pipe flow? So, here I will make 3 cases, that is laminar flow, transitional flow and turbulent flow. Fine. In first I will be writing for pipe flow and second we will be writing for open channel flow. This Reynolds number in the case of pipe flow, for laminar case, Re is less than 2000, then for transitional it is greater than equal to 2000 and less than equal to 4000, while for turbulent it is Re greater than 4000. This will be in the case of pipe flow, but for the case of open channel flow this differs. How come? So, this Re is less than 500 for laminar flow. In the case of transitional it is 500 to 2000 and for turbulent Re is greater than 2000. Fine. So, these with the help of Reynolds number you are able to differentiate in case of pipe flow how come the flow will be laminar, transitional or turbulent, similarly for the open channel flow. Fine. Now, what happens is, why we are considering 2000 here but 500 pipe in case of pipe flow Reynolds number? This is a simple logic. Assume this is your pipe flow, right? It is being filled to the full depth. Now, if I ask you to calculate the hydraulic radius, that is R. This R is the ratio of what? Wetted area to that of your wetted perimeter. So, what is this wetted area? Suppose the diameter of this circular pipe is D. So, the wetted area will be how much? Pi by 4 D square. Fine. And now, if I am asking the perimeter which is being wetted, the length of the boundary or the circumference, you can see the water or any liquid is filled to the full depth. So, in this case it will be 2 pi r, that is the circumference, or you can say pi d. So, from here what you will get? Pi will get cancelled out, d square will get cancelled out with d, and you will get hydraulic radius r is equal to d by 4. So, from here like if it is 2000, so 2000 by 4, that is 1 by 4th time. So, here you will get 500, right. So, this is a simple logic in which you can relate that if it is 2000 in case of pipe flow, it will be 500 for open channel flow. Fine. So, I hope this based on turbulence part is clear to you. After this, we will be moving to the fourth one, that is based on concept of critical flow. Just one thing here, the surface is little bit undulated, the flow is not, the surface, because undulations are in the surface. Fine. So, now moving to the fourth classification, that is based on concept of critical flow. This is very much important because in the upcoming lectures, fine, when you will be moving, you will understand the need of this critical flow. Fine. We will solve a numerical also after this. So, based on concept of critical flow. Now, whenever this critical flow occurs, like I just relate to the initial one, laminar flow was there, transitional flow was there, you used index of classification as your Reynolds number. Now, I am asking, if we are differentiating on the basis of concept of critical flow, how can you say that the flow is critical? There should be some parameter, right, on the basis of which you can say that the flow is critical. So, for this we use Froude number. Froude number. This Froude number in FM, this is like when you will be going to the rapidly varied everywhere, rapidly varied flow and everywhere, this Froude number is important. Fine. So, you should be clear with this. I will explain you slowly. So, pay attention. Froude number is the ratio of inertia force to that of the gravity force. This is the meaning, this is the Froude number in the form of statement. Well, mathematically if I want to write, this Froude number Fr is equal to V root over GT. This you should remember. While I will tell you the most important thing in which you students often make mistake, that is V, you know, that is your velocity, G is your acceleration due to gravity. Fine. And this D is your hydraulic depth. I told you, when I told you regarding the geometric parameters, this is very much important. The reason is, how can you say that the flow is critical? Obviously, in this whole expression, you have to substitute the value of hydraulic depth. Fine. So, D is your hydraulic depth, which is the ratio of your wetted area to that of the top width. Now, the mistake which generally students do is, when I told you regarding the hydraulic depth, I told you that in the case of rectangular channel section, D is equal to Y for rectangular channel sections. Fine. So, what they do is, if I am asking Froude number in the case of trapezoidal channel section or in the case of triangular channel section, they have the habit of putting Fr is equal to V root over Gy. They take it by default that this hydraulic depth is nothing but the depth of flow. But is it true? No, right? Because I told you that this D is your hydraulic depth and it varies with the shape. It is not constant, like for any shape the hydraulic depth will be equal to your depth of flow. No. So, that is the reason D will be equal to Y only in the case of your rectangular channel section. So, other cases you have to remember that D is your hydraulic depth. Now, based on concept of critical flow, when you calculate this Fr, if the value of this Froude number is 1, if the value of this Froude number is 1, then the flow is said to be critical, that is critical flow. Similarly, if the Froude number Fr is greater than 1 and the Froude number is less than 1, then what will happen? This term which I am telling, it will be used most often after this. So, just listen it carefully. Froude number greater than 1 is the case of your supercritical flow. Similarly, Froude number less than 1 is the case of your subcritical flow. Fine. So, now what you can see is, when the given depth is equal to your YC, then it will be the case of your critical flow. Similarly, when the depth is greater than the critical depth, it will be the case of your subcritical flow, and when the given depth is less than the critical depth, then it will be the case of your supercritical flow. Diagrammatically, if I want to explain, I can do it that also for you. Just see, this is the channel bed, this is suppose your depth YC. Fine. Now, what happens is, what I am telling you is, the depth if I am talking regarding the supercritical flow, the depth will be less than, the flow depth will be less than the critical depth. This will be for supercritical. Now, you tell me, if I want to maintain a constant discharge Q and my depth is less than the critical depth, then obviously the velocity will be greater than the critical velocity for maintaining the required discharge. Fine. Now, see for the subcritical flow, what you see here, this is your YC, critical depth. Now, what is happening is your depth is greater than the critical depth. So, this one is your Y. So, this is the case of your subcritical flow. Now, you tell me whether the velocity will be greater than the critical velocity or whether it will be less than the critical velocity. Come on, you can tell me, ma'am, here the critical depth is greater than the given depth. So, obviously for maintaining the required discharge, V is less than the critical velocity, and here V is equal to Vc. So, this is an important classification. Fine, I can say how the flow, you can say that whether it is subcritical, supercritical or critical. You will tell me that Froude number is an index of classification wherever critical flow is concerned. So, based on that you can classify the flow corresponding to it. Fine. So, I hope this is clear to you, this very concept based on the concept of critical flow. Now, moving to the last one, that is based on conceptualizing the flow as 1D, 2D and 3D. I haven't written there that Yc is the critical depth and Vc is the critical velocity. So, if you want you can write it there. Now, this one based on conceptualizing the flow as 1D, 2D and 3D. So, fifth one. Conceptualizing Now, if I ask you, what is your one-dimensional flow? So, when I am dealing with open channel flow, generally we take it as one-dimensional, but actually practically what happens is, you have all the three dimensions. That is, if I am talking regarding one-dimensional, what you will see it, the flow occurs in a single straight direction. Let us assume it as Vx. Fine. Now we are telling that it is two-dimensional. So, what you can say simply, that the flow occurs in two different directions, that is Vx and Vy. Similarly, for three-dimensional, you can draw it like this. And you can see that the flow occurs in three different directions, that is Vx, Vy and Vz. Fine. So, these are the classification: two-dimensional flow occurs, one-dimensional flow occurs or three-dimensional flow occurs. These are the various classification of open channel flow which I have told you. Fine. So, I hope this is very much clear to you. Whether I ask you how you classify it based on critical flow, you should be able to answer quickly that it is based on Froude number. Similarly, based on turbulence, if I ask you, you should be able to say that it is based on Reynolds number. And what happens is, if this is simple 1 marks question, generally it is not asked, it has been asked for ESE and all that. You have been given all these rho, V, dimensions, everything, and you have to tell whether the flow is laminar in case of open channel flow. So, this value that you should remember. Fine. So, now open your booklet, we will see question number 1, MCQ and NET question for your first chapter, that is chapter 1. MCQ and NET question. So now, what is the question? A rectangular channel with bottom width of 3 meter carries a discharge of 8 meter cube per second with a Froude number of 1.5 meter. The Froude number of the flow is, fine. So let me draw first a rectangular channel section. This is your rectangular channel section, fine. Width is B, depth of flow is Y, fine. So now see what you have been given. You have been given the discharge. It has been given to you as 8 meter cube per second. Similarly, you have been given the bottom width B, that is 3 meter, and you have been given the flow depth Y of 1.5 meter. You have been asked to calculate the Froude number. Now, how can Froude number be calculated? You know that Froude number is equal to V root over GT. But in the question, you haven't been given the value of velocity, but you have been given the discharge, you have been given the width and depth of flow. So with the help of width and depth of flow, you can calculate the area, and after that with the equation Q is equal to AV, you can calculate the velocity. So now how can you do it as Q is equal to area into velocity. So velocity is equal to Q by A. So first area is equal to B into Y, that is 3 into 1.5 is 4.5 meter square. So substitute this here, 8 meter cube per second divided by area is your 4.5 meter square. So let us solve this. 8 divided by 4.5 will give you 1.778 meter per second. This is what? This is your velocity. Now for getting the hydraulic depth, I told you earlier also that hydraulic depth is equal to the depth of flow only in the case of rectangular channel section. Let us derive once more. A divided by T. So wetted area is your B into Y and your top width is P. So from here you got D is equal to Y. So what you will do? You will substitute the values here, that is first V root over GY. So velocity is how much you got? 1.778. G is acceleration due to gravity 9.81 and depth of flow Y is your 1.5. So this is your 1.5. So we will solve this. 1.778 divided by root over 9.81 into 1.5. So from here you got the Froude number as 0.4635. This is your Froude number which you can see, 0.4635. Fine. So if I see the option, so option A is your right answer. There could be variation in your decimals because it was coming 1.777. So you would have taken 1.77, but you can see the answer. Then also 1.462 you would be getting something like that. Then also the answer which will be closest for this problem will be your option A. Fine. So I hope this simple problem was there. I hope this is very much clear to you. Just this was a preliminary problem to make the concepts of Froude number clear to you. Fine. So I hope this is clear to you. Thank you.